Rishul, and this is my presentation on the implementation of Nios 2 processor. The main aim of this project is to learn how to implement pipeline processing architecture in Nios 2 using the two examples of dot product and factorial programs. This is the overview which highlights the basic points which we will be discussing in this presentation. The introduction, the instruction types, the design verification of the benchmark programs, results, and conclusion. Altera's Nios 2 is a very versatile. It is actually a soft-core processor that implements programs using logic synthesis. Because of its high performance, it's mainly used for FPGA. The 5-stage pipeline consists of control and data path units, all of them shown here: the instruction fetch, instruction decode, execute, memory access, and write back, the detailed explanations of which are given in the hardware design part of the report. There are three types of instructions in the Nios 2: the I type, the R type, and the J type. The I type, which is immediate, consists of A and B fields, each of 5 bits, that are used to define general purpose registers. Image16 is a 16-bit field for immediate data, which can also be sign extended to 32 bits. OP is a 5-bit opcode which defines the type of operation the Nios 2 will execute. The R type, which is the register type, consists of A, B, and C fields which are of 5 bits each. OPX is an 11-bit field for extended opcodes. The J type, which is jump type, consists of a 26-bit field of unsigned immediate values, and it's only used for the call instruction. The design verification of the benchmark programs, which is the dot product and the factorial, is done using EDA Playground. The functions shown here are generally carried out at the processor level. In this particular slide, the bitwise OR operation is carried out. In the bitwise OR operation, the data stored in image16 has its final value stored back in register R4. In this slide as well, bitwise OR operation takes place, which takes the data in image16 and stores the final value of that in R4. LTW, which is load word instruction, allows computation of byte address by summing the contents in R4 and instruction sign emit value. Mul or multiply instruction consists of a multiplication of R6 and R7 and storing the result in register R8. Here, register R6 consists of value 1, while register R7 consists of value 2. The multiplication of both is 2, which is stored in register R8. Store word, or STW, computes the effective byte address specified by the sum of register 0 and the instruction signed 16-bit immediate value, and stores the contents of R5 into data memory. In the waveform, we can see how contents of R5 is stored in data W, which gives the dot product of the given arrays A and B. Here, the dot product is given as 112, which is in hexadecimal, and converted to decimal gives 274, which is the final value of the given the dot product of arrays A and B. The design verification of the factorial program is very simple. On running the code, we see the input, which is 3, we're defining 3 factorial, gives you an output of 6, being 3 into 2 into 1. The real-time execution is shown on the EDA Playground website. This right here is the code for the dot product program. Test bench being here, and on execution, you get this as the output. This right here is the hexadecimal value of 274, which is also the final value for the dot product of A and B. This right here is a factorial program, which when executed gives you this wave. This waveform clearly defines the input and the output. In conclusion, we went through what Nios 2 is and how its pipeline processor architecture is implemented for two examples, which is DP and factorial, DP being the dot product, given the unique parameters. As seen in the previous slides and also in the playground EDA playground website in real time, you can see that both the programs were successfully implemented. Thank you.